Well, welcome everybody. This is the first of a webinar run by the New Zealand Roundtable for Sustainable Beef. Grant Bunting, I'm the chair of the Roundtable, and thank you all for your registration. And I'd like to also welcome to the session today Frank Mitloehner. Frank is the greenhouse gas guru. Be facilitating the session shortly after this. In terms of the housekeeping, just like to point out that if you do have a question that might come to you during the course of this, then there are two ways to ask that question. You can use the QR code that was sent in at the time you registered, or you can email info@newzealandsustainablebeef.co.nz. and we'll collate those questions and present them to Frank at the end of the session. But GWP STAR, though, is it's starting to attract some attention around the world as it becomes considered to be a more accurate means of measuring methane emissions. And as the science develops, it's certainly important that we look to keep it abreast of some of these trends and ensure that we're able to understand them in the interest of some of the challenges we face here in New Zealand. I'm very fortunate, I said in my introduction, to have Frank Mitloehner with us here today, and Frank's going to discuss GWP STAR and try and bring a New Zealand context to that discussion as well. So Frank's a professor and air quality specialist in cooperative extension with the Department of Animal Science at the University of California, Davis, and is committed to really making a difference to generations to come. He's exceptionally passionate about understanding and mitigating air emissions from livestock operations, and as well as studying the implication of these on about the health of the farm workers and neighbouring communities. He's also very focused on the challenge of the food production challenge that we face from a global perspective, and more so as our world population starts to head up in the vicinity of some 10 billion people by 2050. Frank's also a director of the CLEAR Centre, which carries out research and communications to help the global community understand environmental and human health impacts of livestock. And from that we can make much more informed decisions about the foods we eat and attempting to reduce the environmental impacts at the same time. Frank received a Master of Science degree in Animal Science and Agricultural Engineering from the University of Leipzig in Germany, and a doctoral degree in Animal Science from Texas Tech University. Recruited by the University of California, Davis in 2002 to fill its first ever position focusing on the relationship between livestock and air quality. Frank is well known for sharing his knowledge and research around the world with students, scientists, farmers and ranchers, policy makers, and fortunately for today, all of us. So with that in mind, Frank, welcome, and I hand over to you.
Thank you. Thank you very much, Grant, and it's a great pleasure for me to talk to you today. I was asked to talk about the Rethinking Methane project that we work on, and spend some quality time with you. I hope that you will ask many questions. So the title of my talk is Rethinking Methane, or the Path to Climate Neutrality. So allow me to first break the ice by giving you a little bit of a background of what this whole discussion around greenhouse gases is around, and then I will talk about what we have learned about methane and why it really matters. Also, what some of the policy implications are about the change in narrative that we see happening out there. Before I go into my talk, just really briefly, if you want to revisit some of what I said, there's a video out there. It's called Rethinking Methane. It's on YouTube. If you just Google YouTube and Rethinking Methane, you'll find it. It's a little 5-minute video, but it's easy to understand, easy to share, and I encourage you to do so. So without further ado, going to my presentation here. So what you see on this slide here is the sun radiating down solar beams to the surface of the Earth. Normally that solar radiation would be reflected back into space if there weren't these greenhouse gases that pretty much function like a blanket that you put above our atmosphere, retaining that solar heat in our atmosphere. And this is a very important function that these greenhouse gases have. In fact, without these greenhouse gases, life on Earth would not be possible. It would be too cold. So we need to have this layer of greenhouse gases. The problem, however, is this blanket, this layer is getting too thick because we're adding too many of these greenhouse gases. And that's really at the helm of the problem. So what are these gases? They include CO2, methane, nitrous oxide, and some others. But the main thrust of this talk today is, as I already mentioned, on methane. Methane, in my opinion, is the Achilles heel of animal agriculture, and nobody knows that better than you, because those economies throughout the world that have a lot of grazing animals, such as Uruguay, Ireland, New Zealand, and others, are under the gun for methane emissions. So the question really is, how much of that methane that's generated by your livestock is new and additional carbon, adding to new and additional warming, and what are the relationships between methane emissions on the one hand and warming overall? And I think this is a really important discussion for your context. First of all, you're well aware of the matrix that's currently used, the standard that's currently used when comparing different greenhouse gases. The standard that is being used is called the Global Warming Potential, or GWP 100. Okay, this standard was established back in 1990 when the Kyoto Climate Accord started, and it was really devised because policymakers wanted to know, so how do we compare various sectors of society and their contribution to greenhouse gases? Scientists came up with this GWP 100 and cautioned that there are numerous things that need to be considered when using such factors. They put footnotes underneath those tables. The footnotes were then normally cut off and not considered further. Instead, people just ran with this very simplified way of comparing greenhouse gases using these factors or global warming potential numbers. For methane, both for methane and nitrous oxide, these numbers have changed over the years, but currently the most recent one is a global warming potential factor of 28 for methane and one of 265 for nitrous oxide. So when a source, let's say a dairy or a beef operation or so, produces a given amount of, let's say, methane, let's just say 500 tons in a certain period of time, then all you need to do is multiply the 500 tons times 28, and then you arrive at the CO2e, or the CO2 equivalent unit of that 500 tons of methane. Same is true for nitrous oxide. If you produce 100 tons of that, all you need to do is multiply the 100 times 265, and you arrive at the CO2e. Okay. That assumes, using that global warming potential, that GWP 100, assumes that the only difference across these gases is this factor. And that other than that, they are the same. That they behave the same with respect to causing warming. And whether that's true or not is hotly contested these days. And the reason is that there are differences other than this factor, which are pretty apparent. One of them is that methane is a gas that's not just produced, but it's also destroyed. So when you look at the global picture for methane and how methane is produced and destroyed, you find the following. Here's a global methane budget. On the left side of this budget, you see various sources of methane, including fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so on, all amounting to a total of 560 teragrams, 560. 560 teragrams globally are emitted by various sources. And here's where many people stop the discussion, even though they shouldn't, because globally and locally, we not just have sources, but also sinks, as you see on the right side of this graph. And the total sinks globally amount to 550 teragrams. I repeat myself here, 560 teragrams are emitted, 550 teragrams are destroyed. So in other words, the total in the world is not this large number, 560, but it's the difference between what's emitted versus what's destroyed. And the difference is 10. Still a number that we seek to further reduce, but it's important to provide that part to the discussion, namely that methane is not just produced by sources, but also destroyed by sinks. So what is it that destroys methane at such a large rate? You see here a large arrow pointing downward, and you see the number here is impressive. 515 teragrams are destroyed. And underneath it says sink from chemical reactions in the atmosphere. What are these chemical reactions in the atmosphere that destroy methane? It is a process called oxidation. To be precise, it's called hydroxyl oxidation. I know that's a mouthful, but what it means is that if this fist were a methane molecule in the air, then within approximately a decade, it meets another molecule in the air called a radical. And this radical steals away some hydrogen from the methane and destroys it. And that again happens within a decade. So, in addition to the global warming potential 100 that we talked about just 2 minutes ago, there is this other really important difference that's a direct response, or it's related to what I just said, namely that methane is not just produced but also destroyed. And that leads to differences in the lifespan across these gases. CO2 and nitrous oxide are referred to as long-lived climate pollutants. Why? Because once they go out into the atmosphere, for example, by us burning fossil fuel or by us fertilizing a field or so, then these gases stay in the air for a long time, hundreds or thousands of years. And that's in sharp contrast to methane, which has a lifespan of only 10 years. That's a half-life. So 10 to 12 years is the normal range that people discuss, 10 to 12 years. So that short lifespan is the result of methane not just being produced, but also destroyed. And this is at the heart of the problem. The next slide will show you a very important nuance in this discussion, or a very important principle in this discussion of biological carbon. Biogenic carbon, it's often referred to. And so when you hear of methane, that's CH4, ever wondered where that carbon in the CH4, where that carbon comes from? Well, we have to go back to photosynthesis and what we learned back in school about photosynthesis. We learned that plants, in order to grow, need several things. They need sunlight, they need fertilizer, they need water, and they need carbon. The carbon they need, they receive from the atmosphere. Plants, whether that's grasses or legumes or any other plants, they need CO2 from the atmosphere to build carbohydrates, such as cellulose or starch. So they suck that carbon out of the atmosphere in order to produce carbohydrates such as cellulose or starch. And very important to your context in New Zealand, cellulose is the world's most abundant biomass. Nothing in the world is more abundant than cellulose. And the only animals that can utilize cellulose and upcycle it into animal source foods that human can consume are ruminants. That's the only animal type that can upcycle cellulose and make it into animal source foods. So, but that cellulose originates, the carbon in the cellulose originates in atmospheric CO2. Now, a bovine comes along and eats those carbohydrates, or at least a portion of that, and then emits methane, either in form of belching, it's referred to as enteric fermentation gas, methane, or it's also emitted from its manure. So that methane now makes it into the air, and within a 10-year time frame, that methane molecule will get in contact with a radical in the atmosphere, as I said before, and undergo what's called hydroxyl oxidation. That's a scientific term, hydroxyl oxidation. This hydroxyl oxidation, facilitated by radicals in the air, will convert methane into CO2. But please know this, the carbon in this methane that you see there, in that CH4, that carbon is not new additional carbon added to the atmosphere, but it's recycled carbon. That carbon, that very same carbon molecule in that methane there, originated in atmospheric CO2 before that went into plants. So remember, the carbon from stable livestock herds, is not new additional carbon added to the atmosphere, but it's recycled carbon, and it originated in the form of atmospheric CO2. And that is what it will become within a decade, again, atmospheric CO2. Why is that important? That's important because biogenic carbon is very different from fossil carbon, because fossil carbon goes a different path that I will show you in just a minute. The biogenic carbon cycle is just that, a relatively short-lived cycle of carbon going from the atmosphere into the plants, into the animal, and then back into the atmosphere, the plants, the animal, the atmosphere, the plants, the animal. So this is a cyclical event, very important to remember. And always remember this, as long as your livestock herds stay stable in numbers, you are not adding the relative amount of methane produced because your animals are stable. That means you're not adding new additional carbon, and that does not add new additional warming. And that's what it's all about. Limiting additional warming is all that's about. The Paris Climate Accord, for example, is all about limiting warming to 1.5 degrees centigrade. You know that, and I know that. It's not about limiting the CO2 equivalent amounts from different sectors of society. It is limiting temperatures from rising. That's what is really important. And GWP 100 doesn't predict that. GWP 100 does not predict warming. All it predicts is CO2 equivalencies. That's it. That's not what we really need. And this whole thing will become more intricate in just a minute, but this first cycle is one that you have to remember. So how is this biogenic carbon cycle different from other greenhouse gases that stem, let's say, from fossil fuel use? Fossil fuel being oil, coal, gas that was stored in the ground for a long time are what? That's pure carbon. That is nothing other than plant and animal material that's very old, hundreds of millions of years worth of plant and animal material that accumulated in the ground, and then in a very short period of time, so that's the carbon here in black, in a very short period of time, namely approximately the last 70 years, we have taken about half of that carbon, that fossil carbon, that ancient carbon, out of the ground. We burned it with cars, trucks, trains, planes, ships, power plants, cement factories, and so on. And by doing so, we converted it from carbon that was stored in the ground into atmospheric carbon, because it all becomes CO2. In most developed countries of the world, approximately 80% of greenhouse gases are fossil fuel related. Now, that's slightly different in places like New Zealand or Ireland or Uruguay or so, which have relatively large agricultural sectors and a lot of ruminants. But in general, 80% is a very typical number for most developed countries in the world with respect to the fossil fuel sector contributing greenhouse gases as a part of the total societal spectrum. Livestock in most developed countries emit approximately 5% or so of the total. I know in New Zealand that percentage is relatively larger because you have a large livestock sector and relatively fewer industries compared to many other developed countries. What's also interesting to me is, and something that I've found quite unfair over the years, is that when emission inventories assign the blame, so to say, for greenhouse gases, then they always look at where the emissions are generated. Okay, so when it comes to let's say oil that's pumped out of the ground in Saudi Arabia, then that oil is pumped out in Saudi Arabia, but it's shipped to, let's say, Europe, and they burn it. And so the carbon footprint of that oil, therefore, is blamed to the Europeans that burn that gas, and not to those in Saudi Arabia that drill the gas out of the ground. But when it comes to agricultural goods, the majority of the carbon footprint is associated with where that food is grown. And so if New Zealand, let's say, grows lamb and beef and other commodities, dairy and so on, then the emissions are generated in New Zealand, and New Zealand gets dinged for that carbon footprint. It's not the markets that buy your products that get dinged for it, but it is, in the case of agricultural goods, the location where the emissions are generated. And so I always found that kind of unfair because the emission inventories are very much biased that way globally. So that's very much the disadvantage of countries like Ireland or New Zealand or Uruguay and so forth. So, but please remember here, going back to the difference between biogenic methane, biogenic carbon on the one hand, versus fossil carbon on the other, that the fossil carbon is not cyclical. It is a one-way street from the ground up into the air. And if you want to contrast that on one slide, this slide will do it. On the left side here, you see fossil fuels. Carbon was stored in the ground for hundreds of millions of years. We unlocked it by taking these ancient carbon amounts out of the ground. We burned them, and now they're in the atmosphere. That by far is the most important source of greenhouse gases worldwide. The biological biogenic carbon cycle is different. I just told you about that. Carbon is sucked out of the air by plants. Plants then have some of that carbon stored in above ground vegetation, and a lot of it goes into the below ground vegetation, into the roots. And from there it goes into the soil. And that's a process referred to as carbon sequestration. Carbon sequestration puts away a lot of carbon. How much, we don't really know yet. It's not appropriately quantified in the different areas of the world, but the amount of carbon sequestration putting away carbon is and can be quite substantial. Most emission inventories throughout the world, and I would think New Zealand is within that category, do not really have carbon sequestration as part of their emission inventories, even though I assume that that carbon sequestration would be quite substantive in a country like yours, because there are only really very few land users in the world that can suck carbon out of the air and put it away, lock it away, and that is agriculture and forestry. These are the only two sectors of society that have the ability to take carbon out of the air and put it away, lock it away. Research here in California has actually shown that grasslands can sequester more carbon than forest lands. And that to me is very interesting and of potential importance to a country like yours, where people try to say, you know what, we should just grow more trees. Well, why do they say that? Why do they say let's grow more trees? They say let's grow more trees because they assume that these trees, when they grow up, will suck carbon out of the air, right, and make it into tree mass. And that thinking means that these people who believe that this is a proper way of reducing greenhouse gases, that actually growing trees would lead to a relative reduction in warming, to negative warming, because you're taking carbon out of the air and you're binding it now in the substance of the tree. So this is pretty much a cooling pathway, right? So I'll go back to that in just a minute because this is really important. So people understand that plants will take carbon out of the air and keep it in the plant material. People also understand the general concept of carbon sequestration, but the numbers are not really all that clear yet, and they need to be improved. I think I'll come back later to that very question when people ask me about it. But really briefly here, CO2 goes into those plants. Some of that carbon from the CO2 is now trapped in the ground during carbon sequestration. Bovines, let's say, and other livestock eat part of the plant material, belch some of that methane out. Some of it comes from the manure. That methane is broken down, converted back into atmospheric CO2, adding that CO2 back into the pool of CO2 into the atmosphere. And then from there, plants will suck new CO2 down during photosynthesis. So this is really a cycle on the right side of this graph, and on the left side, it's a one-way street. Nobody should ever compare a car to a cow, okay? It's inappropriate from more than one reason, okay? For more than one reason. But it's often done, and that's why I'm adding it to my presentation. What's really important for you to understand as to why GWP 100 is not appropriate as a unit to be used, for example, to quantify livestock's methane, are the next few slides. And they become a little technical, but it's important for you to get this. So let's start with CO2. CO2 is a long-lived climate pollutant. I told you it has a lifespan of approximately 1,000 years. So let's say you were to drive your car from home to work on Monday, day one. Then you would put new additional CO2 into the atmosphere. So that's, of course, gasoline burned. That's new additional carbon added to the atmosphere. On Tuesday, you drive again, and you add an equal amount of CO2 to the atmosphere, but now it's on top of what you put out on Monday. On Wednesday, you drive again, and so you can see it accumulates, this gas accumulates in the atmosphere. Every time you burn it, you add new additional CO2 to the existing stock. You add new gas, new CO2 to the existing stock, hence the name stock gas. CO2 is a stock gas. It accumulates in the atmosphere, okay? Really important to understand. It accumulates in the atmosphere. Those people who like to use GWP 100 effectively act as if methane were the same, a stock gas, which accumulates in the atmosphere, even though it doesn't. Methane is not a stock gas, methane is a flow gas. Methane is roughly produced and destroyed at equal rates. I showed it on this slide with the global methane budget, but the way this works in general is because methane has a lifespan of approximately 1 decade, a new source of methane will add additional warming to the atmosphere, a new source. But once this source is established, so let's say a dairy was built in 1950, okay? So then the first 10 years in existence of that dairy, it will have produced a new additional amount of methane to the atmosphere. But after the first 10 years, the amount of methane produced and the amount of methane destroyed would have been in balance. That's what flow gases do. They are destroyed roughly at the same rate that they are emitted, as long as the source stays approximately the same. In this case, the herd size. So you can see here, methane is not a stock gas. It doesn't accumulate over time, but it's a flow gas, and it's produced and destroyed at roughly the same rate. Why does that matter in our discussion here? It matters because GWP 100 acts as if methane were a stock gas. The people who pointed this out first, at least to me, were Professor Miles Allen from Oxford University and colleagues. Dave Frame is a name that you might be well familiar with from Australia. He was one of the contributors to this, this blog paper here on the left. Then there were numerous carbon briefs and so on, all different kinds of publications on the topic as to why methane should not be characterized using the GWP 100, simply because it is not a stock gas, it's a flow gas. It's not just produced, it's also destroyed. Peer-reviewed publications have been published, many of them, some in very high impact journals such as Nature and Science and so on, and they're all available to the public. I will now show you 3 scenarios that are critical in the understanding of the differences between GWP 100 versus a new unit called GWP star. So imagine 3 scenarios here. The first one is a scenario by which over the course of 30 years, methane is increased by 35%. Second one is stable methane, or slight reduction by 10%, but let's call that stable methane over 30 years. And the third one is a strong reduction of methane by 35%. How would these three scenarios of increase, a stable, and a decreasing scenario, how would they be depicted by using GWP 100? Here's how. All three scenarios would be depicted with a large increase of CO2 equivalent units. All three, the increase, the stable, and the decrease, would be depicted as a strong increase of CO2 equivalent units. Can that be true? Don't we know that methane is not just produced but also destroyed? So how can it be that even a stable amount of methane leads to an increase of CO2 equivalent units? So something is wrong here. And the new matrix of GWP star shows what's wrong. And you see the unit right here, GWP star, when looking at these three scenarios, predicts the following. A strong increase of 35% methane over 30 years will indeed lead to a strong increase of CO2 warming equivalents, okay? So you can see here GWP 100 and GWP star predict the same thing when methane goes up. They predict the same thing when methane goes up, namely a strong increase of either CO2e or CO2 warming equivalents, okay? No issue there. And that's really what GWP 100 was designed to do, to look at how do these increases in methane over time, how do they compare to other greenhouse gases? And with increasing scenarios, GWP 100 is just fine, as you can see here. But look what happens when you have stable or slightly falling methane. Then the warming equivalence is no longer there. There is no more warming caused by slightly reduced methane over time. I mean, listen to what I'm saying here. A stable amount of methane emitted by a stable herd will not contribute to new carbon. And that means it will not contribute to new additional warming. In fact, a slight decrease here by 10% will lead to a blue area south of the x-axis. You see this here, south of the x-axis. And that means we now have slight negative warming. And negative warming is a fancy word for cooling. Now look at what happens when you decrease methane by 35%. When you do that, you increase or you induce a strong negative warming impact. And that means a relatively strong cooling impact by that decreasing methane source over 30 years. I hope I got everybody excited now, because what this really means is that if we reduce methane, then we can induce cooling. And now look at how different GWP 100 versus GWP star are under stable conditions and under cooling conditions, under decreasing conditions. What I'm telling you is, not just is GWP 100 wrong when we have stable methane, by saying stable methane simply decreases CO2e. It doesn't decrease CO2e. It turns CO2e into from plus to negative, from positive to negative numbers. So not just the quantitative amounts wrong, but the sign is wrong. The sign is wrong. A stable methane leads to zero net increase, and a decreasing methane leads to a decrease and not less of an increase. This is a huge difference between GWP 100 versus GWP star. And the GWP star actually reflects what the warming does of that methane, of that increasing, the stable, or the decreasing methane. GWP star actually predicts the warming. And this is the way it goes. And this is the way that you have to position yourself, because your industry, if you manage to decrease methane, will manage to become an important part of your country becoming climate neutral or going into the direction of climate neutrality. The next slide is the last technical one I want to share, but it's also important. I hope I don't put anybody to sleep here, but it's really important. This slide shows also from Oxford Martin, from our colleagues at Oxford University. First on top, two gases, CO2 and methane. And in this scenario, CO2 and methane both go up. Okay, the one could go up from a power plant because over time it produces more power and therefore more CO2. What happens when you produce more CO2 is shown here at the bottom. You have an exponential increase in the CO2 related warming that's caused by that gas. If you increase methane, let's say, because you're growing your cattle herd, then that leads to an equal increase of the warming caused by that methane. But look what happens when you have constant emissions of CO2, let's say caused by a constant amount from a power plant, or constant emissions of methane, let's say caused by a constant cattle herd. What would these two scenarios do to warming? Well, the constant CO2 would still lead to an increase in temperature related to that CO2 because it's a stock gas. It accumulates in the atmosphere. But look what happens to the methane. A constant amount of methane will lead to constant warming and no additional warming. Remember, that's what it's all about. How do our sectors of society contribute to warming? A constant herd, a constant source of methane does not add new additional warming to the atmosphere. I hope everybody gets that now. That's really, really important. But now comes the scenario that's most important to us here in California and to you in New Zealand. Falling emissions. We all try to reduce emissions in order to reach climate objectives. What happens when we decrease both CO2 and decrease methane? What happens to the related temperature changes? When we decrease CO2, then we still increase the warming associated with that CO2 up until the point that the CO2 is down to zero. Once we reach net zero for CO2, then the warming associated with that CO2 plateaus. That is what it takes for CO2s to stop causing any additional warming. We have to get it down to net zero for it to stop additional warming. Please remember that, okay? If we just decrease it, then we still have increases in temperature. That's how important CO2 is as a climate pollutant. So some people ask me, Frank, do you think methane is a super pollutant? And I say, no, CO2 is a super pollutant. And this is why. Even if we reduce it, our temperatures still go up. We have to get it down to net zero for the warming associated with CO2 to stop. And I tell them, CO2 is a super pollutant, methane is not. Methane is a super opportunity. And they look at me as if I lost my mind. They ask why. And I say, because look what happens when you reduce methane. When you reduce methane, then you have an instantaneous negative warming impact, which is a cooling impact. So that means if you, by whatever means, over several decades, manage to reduce methane, by whatever means, feed additives, changes in productivity, changes in herd size, changes in manure management, however you reduce methane, then that over time will have the impact that you would have by planting trees on your farm. Instead of planting trees and sucking carbon out of the air, a reduction of methane has the same impact. You suck carbon out of the atmosphere. That's what you do when you reduce methane. So a reduction of methane will lead to instantaneous impacts on temperatures, namely a cooling impact. So what kind of research do we do here at UC Davis? How do we know these things, and how do we know what mitigation is doing? So we do put cattle into large structures such as these bovine bubbles here, where we measure enteric emissions and emissions from animal manure. We put flux chambers and wind tunnels onto dairy lagoons, onto livestock lagoons under pretty intensive conditions. We put cattle into head chambers where we measure enteric emissions from cows and other cattle that are fed feed additives, let's say. And we oftentimes work with the state of California, with state agencies like our state EPA and so on. And one last concept I want to share with you, which I find interesting, is that the state of California a few years ago did something very similar to what New Zealand has done. The state of California said, okay, we will not treat short and long-lived climate pollutants the same. They're different, okay? They're different. So our state agency for air quality and climate is called the California Air Resources Board. They said, we don't need to get methane to net zero. That's not needed, but we want to have a reduction of methane because a reduction of methane has an instantaneous impact on climate. And so they worked with the legislature, and the legislature in California came up with a 40% reduction goal for methane. 40. 40% reduction goal to be achieved by the year 2030, so 10 years from now, below 2013 levels. Our farmers went wild when they heard that. They were very worried about it, thought they could never achieve that. Our legislature did something very smart. Instead of using rules and regulations and fines, which I call the cane approach, they used the carrot approach instead, which means or meant that instead of using those fines and so on, they used financial incentives to help farmers achieve those methane reduction goals. So the state of California poured in about $500 million to help farmers invest in techniques and technologies to reduce methane. For example, anaerobic digesters, alternative manure management practices, and others. Technologies like that and techniques were financially incentivized and matched by our dairy industry and livestock industry. And out came a 2.2 million metric ton reduction per year. You see here a dairy, and then you see the lagoon that was previously open. Now it's covered, so now it's an anaerobic digester. It's a covered lagoon, and all the gases that would normally go into the atmosphere are now trapped, and you see them bulging out that plastic here. And now this biogas that's trapped here is not just burned and made into power, but instead this biogas is converted into renewable natural gas, RNG. And RNG is a fuel type that you can put into semi-trucks, which are now run on RNG. If you were a California dairy or livestock producer doing what I just said, converting this biogas from livestock operations into fuel and selling that off to vehicle fleets, then you would get unbelievable credits for doing so, because you would produce the most carbon negative fuel type there is. Carbon negative because, first of all, you avoid emissions from occurring at the dairy, and secondly, you replace the diesel emissions with RNG emissions, which are much cleaner than the diesel emissions. So this double whammy that you are now doing is financially compensated in a major way, This is probably one of the main gold rushes happening in California now. As a result of this policy change, California dairies alone have reduced their carbon footprint, their methane footprint, by 25%. So they were supposed to have a 40% reduction to occur in 2030. They are already today at 25 of the 40. So they're over halfway there. Our dairy industry in the state of California is the by far strongest in the United States. Our dairy industry is over halfway at the methane reduction goal. And that was achieved by the state working together with the farming industry. And what is the overall outcome? The strong reduction of methane, you remember from my earlier graphs, has a relative impact on negative warming, meaning cooling. And that means this cooling impact of methane is now counteracting nitrous oxide and CO2 emissions that also occur on a dairy, to overall get the dairy sector to be a climate neutral sector in a very short period of time to come. I believe that not just the dairy sector, but the beef sector, not just here in California, but throughout the country and throughout the world, can achieve such astounding effects. If policymakers understand we do not have to go to net zero, we have to get to a reduction. The reductions are possible, they are costly, they cost money. And if this is important to a country to achieve, then it behooves them to partner with the farming sector, because oftentimes the financial constraints are such that they just don't have the money to pour hundreds of thousands of dollars into some infrastructure or thousands of dollars into some additive that's not offset by some kind of credit system. So you have to think about, in New Zealand and throughout the world, really, how can you incentivize the reduction of methane? How can you do it such that sequestration is improved, such as a way that enteric emissions are reduced, which is something that we can do. We have shown some enteric emission reductions through research here at UC Davis in the range of 10 to 40, sometimes 50%. So these things are possible. And we can also reduce methane significantly from animal manure. So that is, to me, a real wonderful story, and one that I'm very committed in supporting and communicating. I think, and I just want to say that New Zealand is one of the leaders in the world in this field. I know that you have some aggressive goals, and I do think that you can achieve those goals. I do hope that your policymakers listen to the most recent research from Oxford, and also from your own people like Miles Allen, Dave Frame, and so on, are world leading in this field, and they really have it down. And I just want to leave it with this last slide here. I have two more. This one here showing that I'm on Twitter, and here's my handle, GHG Guru. I also have a blog that might be of interest to many of you. And my center, the CLEAR Center, is on the internet. This is my web address, clear.ucdavis.edu. So with that, I'm super happy to entertain any questions you might have, and thanks very much for listening. I hope it wasn't too dry. Thank you.
Thank you, Frank. That's certainly been most relevant given some of the challenges we face in New Zealand. And look, we've received a lot of questions that we'll work our way through. A number of them very much relate to policymakers and seek to address some of the challenges, as I say, we face here around particularly afforestation and the likes. But I thought maybe in the first instance, some of the more technical questions, whilst we're on the theme, one here in particular, over what time frame is GWP star calculated, and how sensitive is GWP star to recent changes in emissions? So
you can use whatever time frame you choose. I mean, your policymakers might be interested in the 1990, starting 1990. Some of them do. Some of them, like the Californians, said 2013 is the benchmark here. So in my research, I started 1990 and then go through decades. So I have the inventories of 1990, 2000, 2010, 2020, and then predicted to 2030 to help our policymakers in finding what the path is that we would be on if we were to achieve a 10, a 20, a 30% reduction. So I think it makes a lot of sense to go by decades when looking at GWP star. What GWP star really does very well is, first of all, it tells you the rate of change over time of methane, and how that rate of change over time converts into warming. And not just CO2 equivalent units, okay, but into warming. So if you know that in 1990 you were at 100, and in 2000 you were at 95, and in 2010 you were at 90, and now, decades later you are at 85, then you went down from 100 to now 85. And then you can calculate what that impact has been with respect to its conversion into temperatures. And that is really important. So you want to know, are we stable, in which case you're not affecting climate? Are we going up, in which case you would affect climate, pretty drastically so? But if you go down, then you do the opposite. Then you induce negative warming. And for that, you definitely want to get credit, and you want to be incentivized to continue that. Because again, I view methane as a super opportunity for a country like yours.
Thank you, Frank. Again, like there are lots of questions coming in, but it would seem there's a common theme that we'll have to address, with many suggesting that the people that need to be hearing this probably aren't on the call. But just a couple more technical ones. In the first instance, if fossil fuel methane is different from biogenic methane, why does GWP 100 use the same conversion factor for methane irrespective of source?
I don't know. Good question. Good question. And it's very clear that, for example, here in the United States, where a lot of fracking is done, many of these people who do the fracking, they just leave the wells open when they no longer feel that they get enough out of there. And when you leave the well open, then all that fossil methane is coming out, it's pouring out, and it's having a major impact on our climate. That is not biogenic methane that's going through a cyclical situation, but it's that one-way street carbon going from fossil up into the atmosphere. Why they're treating that the same as the methane from a cow is beyond me, because that's definitely different, and it really should be clearly denoted. What's also a huge difference is that livestock systems such as yours have a significant impact on sequestration. I want to know if you quantify the emissions, let's say enteric emissions and manure emissions on the one side, why you wouldn't quantify the sink factor that a grazing system has. Because your vegetation will put a lot of carbon into the ground. How much, I don't know. That really depends upon your specific conditions, but that should be part of any kind of inventory, not just one side, but the other side as well. Always make sure that you keep in mind what a budget is. Any budget has income and expenses. And currently we are treating livestock emissions as if they were only sources of emissions and no sinks. For methane, that's not true. For carbon, that's not true.
No, thank you again. Look, I think just in the interest of time, we're getting a lot of questions around the current environment we face here at the moment, and I think it'd be fair to say a lot of our producers, do feel a wee bit beaten up, and perhaps that some of the rhetoric from commentators and others is such that agriculture is maybe let off the hook. Just with a view to your experience and what we've heard today, what have you found has been successful in engaging with policymakers and governments around trying to encourage a better understanding around the role that livestock could play in the sense of methane?
I think it's really important to acknowledge that your sector has a contribution to greenhouse gases. Okay, so I don't think there's any question that the livestock sector is a significant contributor to greenhouse gases. I would emphasize that that's the case. I would emphasize the importance of methane as a potent greenhouse gas. I would also emphasize the fact that you have conducted life cycle assessments to accurately quantify how much you produce. I would then emphasize the fact that you have generated goals for further reductions, so that you show that you care about this topic. Okay, you're not trying to deflect. You're not saying, "Hey, it's not true. We're not part of the problem. Leave us alone." That's not what you're saying. But what you are saying, in my opinion, what you should be saying is, we are a sector that contributes to it. We have acknowledged, we have quantified it. We have set goals for the future. We want to be subjected to a unit that accurately reflects the warming impacts we have. GWP 100 doesn't do that. GWP star does do that. And then we want to get, if we make leeway and if we reduce emissions, we want to be incentivized and credited for those emissions. That's really important, and that's not asking too much. Some people say, let's just incentivize farmers to plant trees. I already said that earlier. Well, okay, that's fine. But why would you then not incentivize the same thing when it comes to methane? It does the same thing and pulls carbon out of the atmosphere. So please do incentivize the reduction of methane from livestock, because it does the same thing as planting trees. But planting trees takes forever for these things to really suck a lot of carbon out of the atmosphere. And as far as I know, everybody is saying we are running out of time. So planting trees now would do what in what period of time?
Good. Just on that, the follow-up question, the reference has been made here that perhaps, again, some of the issue here might well be that those that seek to find themselves in this position aren't always well informed, and the easy answer at that point is to follow the lead of others. If that lead, in fact, is coming from the likes of the IPCC, are you aware of any work that they might be doing that is reflective of a change in how they measure greenhouse gases?
Well, the IPCC is not an entity that recommends one specific standard, such as GWP star or GWP 20 or GWP 100. They have assessment catalogs in which they list all of them, and then you pick whatever is most relevant in your policy environment. In my opinion, New Zealand would be well served by looking at what the impact of your livestock sector has been over the years, whether or not you went this way or that way or that way, whether you increased, decreased, or kept stable. And it's really important to always keep your eye on the ball. And the ball is warming. It's not about a carbon footprint. It's about a warming footprint. And what is the warming footprint of New Zealand's beef and dairy and other industries? That's the question. And you will never get the answer to that by using GWP 100. But you will get the answer by using GWP star. Why wouldn't you? This is not some kind of greenwashing exercise or creative accounting. In fact, GWP star uses GWP 100 in its formula. It uses the same thing in its formula, but it looks at it over time. So be smart about it, because your livestock sector is actually very important to New Zealand. And if you run a policy that makes your farmers give up, then guess what happens? Then whatever livestock products are not produced in New Zealand anymore because farmers are disgruntled and give up, will then be produced elsewhere in the world. And whether these other places that then pick up the slack, whether they will be as efficient and as environmentally conscious as your farmers are, remains to be seen. This is called leakage. And leakage is the last thing you want. You want the farmers who do a really good job to do a really good job. And New Zealand farmers are known to do a very good job. So please incentivize those people who do a really good job to keep doing it and quantify it appropriately. And I would recommend to incentivize it for them to work even harder along those lines.
Yeah. Look, Frank, I'm sure that very impassioned case you've made is very well understood by the majority of people that have listened in today, and I certainly hope we are able to leverage that as we face some of the challenges we've got. But certainly your points made around the methane cycle, afforestation in terms of trees, and perhaps the desire for people to have a fresh perspective on how emissions are viewed in New Zealand is well overdue. Look, regrettably, we're running out of time, or we have run out of time almost, and there's a large number of questions here that we just simply won't get to. But in general sense, the rhetoric is the same. And it would seem, as I would expect anyway, your time today has been exceptionally well received. So, Frank, on behalf of the New Zealand Roundtable for Sustainable Beef, I do thank you for giving up your time and presenting today. And we certainly look forward to following you and others as you seek to sort of provide this basis of education. So, thank you, Frank.
Ron, thank you very much. One last word to your members. And that is, please know that you're not alone. You might think that you're singled out and it's only happening to you. It's not only happening to you. Last week, I talked to farmers in Wales, before that in Ireland, in Uruguay, in Argentina, all over the world. Farmers are under the gun. There's a global situation around farming and farmers being put into some very tough spots, undeserved in most cases. And I think it's time to wake up to that and to become more active. And I think that what you're doing is the right thing, to inform yourself about new narratives around that, new policies, and become active and inform the public and tell them that you care. Tell them that you care, that the environment is important to you, and being a good player is critical to you. It's your legend, and you are more interested in your legend than anybody else out there. So the best of luck to you. I'm very thankful that you invited me, and if you ever want to talk to me again, I'm glad to do it at any given time.
Thanks, Frank. Bye now. Cheers.
You're welcome. Bye-bye.